Good evening, children.
Good evening, ma'am.
Good evening, ma'am.
Good evening, ma'am.
Good evening, children. All of you keep your cameras turned on. Kindly blur your background. If you're not able to blur your background, make sure that there's no movement to the background. Kindly blur the background, else make sure that there is no movement to the background. Yeah, so your cameras must be turned on throughout the meeting. Do not force me to repeat this instruction. Your cameras must be turned on throughout the meeting. Giant, Gautam.
Ma'am?
Please turn on your video.
Ma'am, it's not awning, ma'am.
Okay, from the next class. All right.
Yes, ma'am.
Yeah. Please fix that. And from the next class, make sure you're able to turn on your camera.
Ma'am, 1 minute, ma'am. I will come in my desktop, ma'am.
All right. Well, I was just waiting for the others to join, children. So it's time. Let's begin today's session. I've shared my screen. Is it visible? Is my screen visible, children?
Yes,
I've shared my
ma'am. Yes, ma'am.
Yes, ma'am.
All right. So this was your homework. Every whole number. I hope all of you tried this. Netra, answer the first one. Every whole number is a natural number. True or false?
True.
True. Every whole number is a natural number.
Yes, ma'am.
It's
Ma'am,
true.
can I try the second one?
One second. Every whole number. So, children, 0 is a whole number. Is it a natural number?
No, ma'am. No, ma'am.
No. 0 is a whole number. All of you disable your mic. Keep your mics muted. Keep your mics muted. Unmute only when you want to say something. All right. So 0 is a whole number. See, every whole number, 0 is a whole number. But 0 is not a natural number. The statement is every whole number is a natural number. Yeah, every whole number other than 0, 0, 1, 2, 3, 4, 5, all these are natural numbers. All these are natural numbers going on like this. All these are natural numbers, but 0 is a whole number, which is not a natural number. See here, this is the collection of whole numbers. This is the collection of whole numbers. All these are natural numbers. All these are natural numbers. But 0, which is a whole number, is not a natural number. So the first statement is true or false, children?
False, ma'am.
False. It's false because the exception is 0. Just for 0. Only that. The other whole numbers are all natural numbers. But 0 is a whole number which is not a natural number. So just for that reason, it is false. Just for that reason, it is false. The second one, every natural number is a whole number. Let's write the collection. Every natural number. Every natural number. Yeah, it is a whole number. 1 is a natural number. It is a whole number. 2 is a natural number.
Natural number starts from 1. It's a whole number.
No. Kindly answer only when requested. So the collection of whole. This is the collection of natural numbers. This is the collection of natural numbers, and every natural number is a whole number. See, this is a natural number. It's a whole number. This is a natural number. It's also a whole number. The next one, every natural number is an integer. All right, I think the best thing is, I will give out the answers. Just check if you've got it right in your books. So that I can even explain the reason why. Every natural number is an integer. Every natural number. So I have to write the collection of natural numbers. So let me write the collection of natural numbers like this it is. All right. Every natural number is an integer. This is a natural number. Is it an integer? Yes, it's an integer. What are integers? See, integers start like this, right? -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. It goes on like this. It goes on like this. This is the collection of integers. Now, every natural number is an integer. Yes, all natural numbers are integers. Let me write it again. Let me write it again. See here, this is the collection of integers. We don't know from where it starts. -4, -3, -2, -1, 0, 1, 2, 3, 4. The collection extends indefinitely like this. This is the collection of integers. Now, every natural number is an integer. See here, all these are natural numbers. All natural numbers, yes, are integers. They're all positive integers. All natural numbers are positive integers. Can you see? We have natural numbers in the collection of integers. In integers, we have natural numbers. So every natural number is an integer. But the other way is not true. Every integer is not a natural number. Because see, -4 is an integer. But it's not a natural number. The other way, the statement the other way is not true. -4 is an integer. But it's not a natural number. -4 is not a natural number. Similarly, 0 is an integer. 0 is an integer. It's not a natural number. So this statement is true. Every natural number is an integer is true. Every natural number is an integer. I'm writing the collection again. I'm writing it again. It starts from somewhere we don't know. So -4, -3, -2, -1, 0, 1, 2, 3, 4 goes on like this. And we see natural numbers here in the collection of integers. We see natural numbers in the collection of integers. So every natural number is an integer. But every integer, see here, every integer is not a natural number. So this statement is true. Every natural number is an integer is true. Please look into your books and check if your answer is right. Again, every whole number is an integer. The next one, every whole number. So it starts from here, every whole number, 0, 1, 2, 3, 4, and so on. Every whole number is an integer. Yeah, see here, all the whole numbers, all these are whole numbers and they are integers. Please write the collection, only then you can decide correctly without going wrong. Please write the collection. Please write the collection. Every whole number, see, these are whole numbers. These are whole numbers. They extend indefinitely like this. These are whole numbers. And every whole number is in the collection of integers. So every whole number is an integer is true. True. Every rational number is an integer. Every rational number is an integer is false. Because 2 by 3 is a rational number, but it's not an integer. Every rational number is an integer. 1 by 2 is a rational number. Integer by integer form, no? Numerator is an integer, denominator is an integer. Integer by integer is a rational number. -5 by 9 is a rational number because it has the integer by integer form. It's a rational number. Integer by integer is a rational number. So if you take an example like that, so -5 by 9 is a rational number, but it's not an integer because it's not in this collection. It's not in this collection. So what do we have in the collection of integers, children? You can go back and see the definition of an integer. An integer will have all natural numbers. An integer will have, that is the collection of integers, will have all natural numbers, their negatives and 0. So if a number should be an integer, let me remind you of that again. Let me remind you of that. See here, all natural numbers, their negatives. So -1, -2, -3, -4, -5, they're negatives, including 0. So this is what we have in the collection of integers. We have all natural numbers. We have their negatives and 0. So these are the three things. If you want to check if a number is an integer, it should be a natural number, or it should be the negative of a natural number, or it should be 0. If a number is an integer, it should be a natural number, or it should be the negative of a natural number, or 0. It should be one. It should belong to one of these three categories. Then it's an integer. If you call a number an integer, then that number is either a natural number, or it's the negative of a natural number, or it is 0. It should fall under one of these three categories. So here the statement is every rational number is an integer. So we take an example like -11/12. It's a rational number, but it's not an integer because it is not a natural number. It's not the negative of a natural number. It is not 0. So every rational number is an integer. Every rational number is an integer. Is true or false? Class, is it true or false?
False.
Very good. Every rational number is an integer is false. There are rational numbers which are integers. Now, for example, 5 is a rational number because 5 is 5/1. 5 is a rational number. 5 is 5/1. 5 is a rational number because it's 5/1, and 5 is an integer. So there are rational numbers which are integers, but all rational numbers or every rational number is not an integer. A 0 is a rational number. True or false?
True, ma'am.
True. 0 is a rational number because it is 0/1. Every integer is a whole number. So again, let's write the collection. -4, -3, -2, -1, 0, 1, 2, 3. It extends indefinitely. Every integer is a whole number. Can you see here? Is every integer a whole number?
No, ma'am.
Why?
No, ma'am.
Tell me an integer which is not a whole number.
Ma'am, -1, -2.
Yeah. The statement is every integer. That means if you select any integer, it is a whole number. Select an integer, -4. Is it a whole number? No. But there is another whole number, 0, or there is another whole number 1, 2, 3, which is also an integer. But what is the statement? What is the statement? Every integer is a whole number. Every integer you take, so you take the integer -2. It's a whole number. No, it's not a whole number. So this statement is false. But the converse is true. Every whole number is an integer. Every whole number, because 0 whole number, it's an integer. 1 whole number, it's an integer. 2 whole number, it's an integer. Every whole number is an integer. But the other way, every integer is not a whole number. So the statement is false. The next one, every rational number is a whole number. Every rational number is a whole number. So 4/5 is a rational number, but it's not a whole number. Every rational number is a whole number. 4/5 is a rational number, but it's not a whole number. So false. Every integer is a rational number. Is this true or false, children? Every integer is a rational number. True or false?
False.
False, ma'am.
Every integer.
Ma'am, it's true, ma'am.
Every integer is a rational number. All if you think about it, every integer is a rational number. Think about it.
True, ma'am.
Ma'am, it's true.
Yeah, it's true because every integer can be written as that integer by 1, correct? Every integer in the denominator of every integer, you can say 1. So every integer is a rational number. Here. Every integer, see the collection here. Every integer, see -4, this -4, -3, -2, -1, 0, 1, 2, 3, 4. Every integer is a rational number. Yeah, because every integer is by 1, by 1, by 1, by 1. This can be for 0, you can write any denominator like 1, 2, 3, 4, 5, anything you can write by 1, by 1, by 1, by 1. Yes, every integer is a rational number because every integer can be written in the P by Q form. Every irrational number, next one. So this is true. This is true. Every integer is a rational number is true. Every irrational number is a real number. We have to come to that. So we'll discuss only till here because I haven't introduced irrational numbers to you. I'll show you the answers, like children. Quickly check your answers. The slide has the answers. I'll give you about 2-3 minutes. Please check your answers. Done, children?
Yes, ma'am.
Yes, ma'am.
So children, see, to answer these statements, you have to be very clear with the definitions of a natural number, whole number, integers. That collection should be clear in your mind. Only then, see, without having the definitions clear, you cannot attempt to answer these statements correctly. You must be very sure. You must be very sure about whole numbers, natural numbers, integers. See, we may be in 9th standard, but we still tend to get confused with integers and rational numbers. Please make that clear to you. See, so the term integers means natural numbers. One thing is natural numbers. Then they're negatives and 0. That's all we have in the collection of integers. What do we have in the collection of integers? All natural numbers. All natural numbers. Then they're negatives. So all natural numbers meaning 1, 2, 3, 4, 5, 6 and so on. They're negatives meaning -1, -2, -3, -4, -5, -6 and so on. And 0. This is what we have in the collection of integers. All natural numbers, their negatives and 0 forms the collection of integers. So you know what natural numbers are, whole numbers are, integers and rational number. Rational number means P by Q form. Integer by integer form. Integer divided by an integer. Integer by integer form is a rational number. Okay. The rest of the statements, we'll see the answers later, children. But just if you're curious, you can just see the answers in the slide. If you want to know the answers, I've already put up that slide for you. You can see the answers there. Okay, this is the next slide. This is the next one. You can make a note of the answers if you want to think. You can make a note of the answers. Done, children?
Yes, ma'am.
Yes.
All right, children. So we have discussed only till I think the 9th one. Now let's understand irrational numbers. That's where we stopped in the last class. So now what we understood about rational numbers is that any number that has a P by Q form, integer by integer form, is a rational number. If a number has an integer by integer form, then it's a rational number. Irrational numbers do not have a P by Q form. That's all. We'll see the definition, but now just understand, just get a picture of what irrational numbers are. Irrational numbers, they don't have a P by Q form. They don't have an integer by integer form. Rational numbers have an integer by integer form. See, children, denominator is not 0. That now you know. So I will not be saying that. I'll only say integer by integer form. I will not be mentioning that the denominator should not be 0. Now we all know that. So if a number has an integer by integer form, it is a rational number. If a number does not have an integer by integer form, it is an irrational number. Then how do these numbers look like? If they don't have an integer by integer form, then how do these numbers look like? So now one more thing is that irrational numbers will have a non-terminating, non-repeating decimal expansion. We saw that rational numbers okay, so we saw that a rational number has two types of decimal expansion. Either it's a terminating decimal or it is a non-terminating repeating decimal. Irrational numbers, they don't have, this one has a P by Q form. This one does not have a P by Q form. It does not have an integer by integer form. We'll see how will the numbers look. We'll see that. Now these numbers have a non-terminating, non-repeating decimal expansion. Let me write it again for you so that it's clear. Let me write it again. See here, rational numbers have a p by q form. They have a p by q form, integer by integer form. And you know that when it's an integer by integer form, it means it's division there. P divided by q. So when you divide p by q, I told you this in the last class, when you divide p by q and the division comes to an end with a zero remainder, then the quotient is a terminating decimal. When you divide p by q and the division comes to an end with a zero remainder, then the quotient is a terminating decimal. And upon division, upon dividing, when the division does not come to an end with a zero remainder, the quotient is a non-terminating but repeating decimal. I told you this in the last class. So this is about rational numbers. P by Q. So division is possible here. Division comes to an end with zero remainder, terminating decimal. Quotient is a terminating decimal. If the division does not end and it goes on forever, the decimal expansion also will go on forever. That's why non-terminating, it does not stop. Non-terminating, repeating decimal expansion. Now, irrational numbers, they don't have a p by q form. They don't have an integer by integer form. So no division here. In irrational numbers, there is no division. There's no division here. Okay, now these decimals are non-terminating, non-recurring or non-repeating. Non-terminating, non-repeating. Now class, what are the three types of decimals? Devadarshini, what are the three types of decimals? Krishmika, what are the three types of decimals?
Ma'am, terminating decimal, non-terminating, repeating decimal, non-terminating, non-repeating decimal, ma'am.
Okay, which two decimals are rational numbers?
Terminating decimal and non-terminating repeating decimal, ma'am.
Are rational numbers. Very good. Thank you. Raja, what kind of decimal expansion does an irrational number have?
Ma'am, non-terminating, non-repeating or recurring decimal expansion.
Okay, okay. Udanshri, does an irrational number have a p by q form?
No, ma'am, they didn't have a P by Q form.
They don't have a p by q form. And do rational numbers have a p by q form, Udanshri?
Yes, ma'am, they have.
They have a p by q form.
Yes, ma'am.
Okay. Now, the next question is, from where do these then see now rational numbers, we know that they come from a division process. If the number has a p by q form, then by the result of division, we get a terminating decimal or a non-terminating repeating decimal. Now, from where do we get this non-terminating, non-repeating decimal? There is no division process because there is no p by q. Then from where do we get such numbers? So these numbers are the values of square root of 2. That is the square root of an imperfect square. Last year we've come across this chapter, square roots and cube roots. Now when I say square root of 4, listen to this very carefully, children. Listen to this very carefully. You can make a note of this. Rational number C, you can just make a note of this. You can write it now along with me. I'm doing it again for you because this is very, very crucial for the whole chapter. Rational numbers have a p by q form. This is just for our understanding. Terminating decimal or a non-terminating repeating decimal. Irrational numbers, they don't have a p by q form and their decimal expansion is non-terminating, non-repeating. Please make a note of this. You can put it in a cloud. Make a note of it and put it in a cloud, or whatever way I don't have place to make a cloud. Okay, so you can just put it in a cloud. You can use sketch pens. You can, you can put the cloud using a sketch pen. Now don't run for your sketch pen. It's okay. You can keep all that ready for the next class. You can use highlighters so that when you turn the page, that's catchy and you don't miss to read that. I'm not able to see Krishmi. Are you there in the meeting, Krishmi? Udanshri, you have logged in from 2 different devices, is it?
No, ma'am, I'm in one device only.
But I can see you. I can see 2 of your windows.
1 minute, ma'am, I will check.
Maybe you've logged in from your phone also.
No,
You're
ma'am.
connected to our office. Okay, fine. I can see 2 windows of yours. Yeah, Shri Krishmi, I can see you now. Understood, Shri Krishmi? Rational numbers, irrational numbers. I can't hear you.
Ma'am, the screen is hiding.
All right. Fine, children. So this much is clear. So let's continue. Ready, Devadarshini, for the next?
Yes, ma'am.
Clear so far?
Yeah, ma'am.
Very good. All right, children. So now, is 4 a perfect square?
Yes, ma'am.
Is
Yes,
4
ma'am.
perfect?
Yes, ma'am.
4 is a perfect square.
Yes, ma'am.
4 is a perfect square. So what is the square root of 4?
2, ma'am.
2, ma'am.
2 into
Square root of 2. We say plus or minus 2. The square. Okay. Now so far you've come across the positive, only the positive square root. So let's take only that. Square root of 4 is equal to 2. And what is 2? 2 by 1. P by Q. It's a rational number. So square root of 4 is a rational number. Is a rational number. Rational number. Why? Because square root of 4 is nothing but 2. And 2 is 2 by 1, which is integer by integer. And so it's a rational number. So it's a rational number. Somebody's mic is enabled. Disable your mic. So now when I take 9, square root of 9. Square root of 9 is 3.
3.
And 3 is by 1. And that is integer by integer, which is a rational number. Is that fine?
Yes, ma'am.
yes, ma'am.
Yeah, now take 10. What is the square root of 10?
5, ma'am.
Yeah, ma'am.
So there is no natural number. There is no natural number. Now, why did we say the square root of 9 is 3? Because 3 into 3 is 9. Now, there is no number. Now, 4 into 4 is 16. That means all the numbers between 9 and 16 are not perfect squares. See, because 3 into 3 is 9. And then 4 into 4 is 16. So the numbers between 9 and 16 are not perfect squares. They are not perfect squares. Because after 3 into 3 is 4 into 4, which is 16. So 10, 11, 12, 13, 14, 15, these are not perfect squares. So 10 is not a perfect square because there is no natural number which when multiplied by itself can give you 10. So square root of 10 is an irrational number because when you find, so now last year we had the long division method of finding the square root of an imperfect square. So when you find the square root of 10, the square root of 10, okay, the value of square root of 10 is 3.16227766016. It goes on like that. It goes on like that forever. The square root of 10 is the value of square root of 10. Now see, a square root of 9 is a rational number because square root of 9 is 3 and 3 is 3 by 1, which is integer by integer. 3 is an integer, 1 is an integer. So it's a rational number. But when you take the square root of 10, there is no number which when multiplied by itself can give you 10. And the value of root 9 is 3. You know what the value of root 10 is? This one, 3.16227766016. It goes on like that. And what you will observe is that there will be no digit or a set of digits repeating itself. Like in, again, recall from the last class about non-terminating repeating decimals. So we said 2.141414. If it goes on like that forever, we say 2.14 recurring. If it's 2.141414 goes on forever like that. So we say 2.14 recurring, 14 recurring. So here we see one digit or a set of digits here, 1 and 4. These two digits, 1 and 4, they repeat itself. That will not happen here in the case of the square root of 10. You cannot put a bar like this because there is no pattern. There will be no pattern. No digit or a set of digits will repeat itself. See here, you get 1 here, right? You have 6 here. After 6, it is 2277. But after the 6, it is 6016. After the 6, you have 2277. But after the 6, you see 6016. There is no pattern. There is no pattern. You cannot say that it's not like 2.1476, 1476, 1476 forever. So then you can say it's 2.1476 recurring. Non-terminating repeating decimal. Non-terminating because it goes on like this. And repeating because 1476 repeats itself. But in the case of root 10, which is 3.16227766016 and going on like this, there is no digit or a set of digits that will repeat itself. There's no pattern. You cannot write 3 point something and put a bar on it. There is no pattern. And hence this is a non-terminating. Non-terminating because it goes on forever. This value goes on forever. So non-terminating. Non-repeating because there is no digit or a set of digits repeating itself. So non-terminating, non-repeating decimal. Non-terminating because the value goes on like this. Non-terminating, it does not terminate, it does not end. Non-terminating. Non-repeating because there is no digit or a set of digits that's repeating itself. Non-repeating, decimal. So similarly, the value of square, the cube root of, let's say the cube root of 27. What is the cube root of 27?
9.
From next class, I'll remove all those students whose videos are turned off. I'm not rude, but this instruction was given at the start of the class. Yeah. So the cube root of 27, children. What is the cube root of 27? 3. Cube root of 27 is 3. The cube root of 27 is 3. And what is 3? 3 by 1. Integer by integer. It's a rational number. It's a rational number. What about 125? What's the cube root of 125?
5.
5. Because 5 into 5 into 5 is 125. Cube root of 125 is 5. So cube root of 125 is 5 and 5 is 5 by 1, integer by integer, rational number. But when we say cube root of 125, there is a natural number 5, which when multiplied by itself 3 times produces 125. And hence 125 is a perfect cube whose value is 5. 125 is a perfect cube whose value is 5. Because 125 is a perfect cube because there is a natural number 5, which when multiplied by itself 3 times produces 125. So now when you start from 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Now all the numbers lying between 1 and 8 are imperfect cubes. They are not perfect cubes. They are not perfect cubes. They are imperfect cubes. 1 is a perfect cube. 8 is a perfect cube. 27 is a perfect cube. 64 is a perfect cube. All the other natural numbers lying between 1 and 8. All the natural numbers lying between 8 and 27. All natural numbers between 27 and 64. All those natural numbers between these numbers are imperfect cubes. 64 is a perfect cube. Is that fine, children? Perfect cubes and imperfect cubes?
Yes, ma'am.
Very good. So now tell me, is 15 a perfect cube?
No, ma'am.
No, ma'am.
Is 15 a perfect cube? No, it's not a perfect cube. It's an imperfect cube because there is no natural number which when multiplied by itself 3 times can give us 15. 5 threes are 15. But not like that. We want one number into itself 3 times to give us 15. There is no such number. So 15 is, it's not a perfect square also. It's not a perfect cube. So the cube root of 15. The cube root of 15 is an irrational number. That is the value of cube root of 15. I don't have a scientific calculator to give you the value of cube root of 15. So the value, whatever is the value of cube root of 15 is a non-terminating, non-repeating decimal. It will have some value, right? That value, the value of cube root of 15 is a non-terminating, non-repeating decimal. That means the decimal value will go on and on. It's non-terminating and there is no digit or a set of digits repeating itself. Non-repeating decimal. So this is how we get irrational numbers. Irrational numbers are the results of the square roots of imperfect squares, cube roots of imperfect cubes, and so on. The square root of an imperfect square, its value is an irrational number. Or the cube root of an imperfect cube. It's not a perfect cube, it's an imperfect cube. So the square root of an imperfect square, the cube root of an imperfect cube, all these give rise to irrational numbers. These values are all irrational numbers because they will have a non-terminating, non-repeating decimal expansion. Is that fine, children?
Yes, ma'am.
Yes, ma'am.
Yes.
Now
ma'am.
let's understand. Let's see if we have understood, you know what, I'm using the short forms. Just a minute, children. Just a minute. Danya, are you in the meeting, Danya? Danya?
Ma'am, she's not in the meeting.
She's not in the meeting, right? She joined. All right. So children, now let's understand. Let's check if we have understood. You know, these three decimal expansions: terminating decimal, non-terminating repeating decimal, non-terminating non-repeating decimal. Okay, let's check. Tell me, 2.175. Is it a terminating decimal? What is it? You should give one of these three names. Is it this, this, or this? Yes, anyone can answer. It's an open question.
I'm terminating decimal, ma'am.
Terminating decimal because it stops. That's all. 2.175. That's all. 2.175. What do you mean by the word terminate? It comes to an end. It comes to an end. 2.175 is a terminating decimal. Yeah. Now if I say 2.17517, listen very carefully, children. 175, 175, 175. What kind of a decimal is this?
Ma'am, recurring decimal.
Non-terminating repeating decimal.
Non-terminating recurring decimal.
Yes, Sindhu.
Ma'am, non-terminating recurring decimal, ma'am.
Okay. Non-terminating recurring. Rishmika.
Ma'am, non-terminating recurring decimal, ma'am.
Non-terminating recurring. Gautam.
Non-terminating
Non-terminating recurring or non-recurring?
recurring, ma'am.
Recurring. Jayant.
I'm non-recurring, non-recurring, man.
Rishmi. You have to unmute yourself and then answer. 2.175, 175, 175. Okay, so majority of us feel it is a non-terminating but repeating or recurring decimal, which is incorrect, which is wrong. So I win. I wanted to win and I won. So now correct your answer. Think again and tell me. See, sometimes I might mislead you. You all may be right. I might simply say it's an incorrect answer. So don't change your answer. Think again, but you stick to what your mind says. Now tell me, does anyone want to change? No? So all of you say it is a, or most of you who have shared your answer say it's a non-terminating repeating decimal. Yes or no?
Yes.
Okay. So that means I have really won.
Yes, ma'am.
All of you are incorrect. It is a terminating decimal. It ends here. I did not do this. It ends there. I didn't say 2.17. That is the difference. I just said 2.175, 175, 175, 175. That's it. I stopped there. I stopped. When I stop, it's a terminating decimal. But if I don't stop, I say 175, 175, 175. I'm tired writing 175. So I just use these dots. Because I know how long can I keep writing 175. So I use these dots. That means these indicate it's only when I say show this, it is non-terminating. And it's repeating because 175, 175, 175. It's repeating. Non-terminate. Non-terminating is only when you see these dots. Non-terminating. Repeating is because repeating. Decimal. Now this is, see, even if I write 2.175, 175, 100 times, it is a terminating decimal because it ends there. If I keep writing this, I keep writing some 100 times, it is still a terminating decimal because it ends there. Don't think if it's too long a decimal, then it is non-terminating. It's not like that. It ends there. Even if I write 100 times, it ends at some point, it ends. So it's a terminating decimal. It may be a very, very lengthy decimal, but it ends somewhere. So it's a terminating decimal. If I use the dots, now after this, so like I just told you, I'm just repeating that. So if I say 175, 175, and you know, I don't want to keep writing. So this is a non-terminating repeating decimal. Now I think you've become smarter. Let us see if you can tell me correctly. Now see here, 3.173, 174, 175, 176. What kind of a decimal is it? Is it terminating decimal, non-terminating repeating decimal, non-terminating non-repeating decimal?
Terminating decimal.
Terminating decimal.
It's a terminating decimal because it stops here. Don't see there should be pattern and all that. Nothing. Does it stop somewhere? Yes, it stops. It's a terminating decimal. Now, if I say 3.173, 174, 175, 176 and goes on like this, do you see any pattern? Can you put a bar on any digit? Okay, let me say the difference. If I say, if there's a pattern, I should repeat that pattern at least once. See, now if I say 2.3, like 173, and I just put dots, you cannot assume that 173 is repeating. You cannot assume 173 is repeating. I didn't say that. So if I want to say that 173 is repeating, I must say 173 and at least once more I must write that and then put the dots. This indicates you should write that pattern at least once again. 2 times it should be there. At least 2 times. Only then you get an idea when you read this 3.173. Again 173. Oh, okay. So this is 3.173 recurring. Do we get that, children?
Yes.
So if I put 3.5 and once more I write 5 and then put the dots. That means 5 is repeating. Because, yeah, I've indicated that, see, 5 and again 5. So that means 3.5 recurring. Put a bar on that digit or the set of digits that repeat itself. Don't put the bar like this. The bar comes only after the decimal point, not before the decimal point. So now 147.005005. What kind of a decimal is this?
Non-terminating repeating decimal.
Non-terminating repeating decimal. How can you express this? 147 point
005
005 and
recurring symbol.
a bar on top of 005. A bar on top of the digit 005, correct?
Yes.
All right. So this one is a non-terminating repeating decimal. Now this one 147.147, 148, 149, 150, and so on like this. What kind of a decimal is this?
Non-terminating.
Non-terminating.
Non-terminating repeating decimal. But if I write point, somebody's mic is enabled. What kind of a decimal is this?
Terminating decimal.
Non-terminating decimal.
Terminating decimal. This one is a terminating decimal. So see, the difference lies in the dots. The difference lies here. See, if I don't say that, it's a terminating decimal. If I say that it's a non-terminating, Non-repeating because I have not shown any pattern. There is no digit or a set of digits that's repeating itself. So non-terminating, non-repeating decimal. But this one is a non-terminating because see the dots. So non-terminating. Repeating because 005, 005. So non-terminating repeating decimal, which can be written as 147.005. These are the 3 digits that repeat and a bar on it. Just a minute, children. All right, children. So now what you should understand is irrational numbers. Remember this much, irrational numbers are outcomes of square roots of imperfect squares, cube roots of imperfect cubes, and so on. Now, what is the fourth root of, what's the fourth root of 64? 1 minute. Not the fourth root. What is the sixth root of 64? What is the sixth root of 64? Tell me one number which when multiplied by itself 6 times can give us 64. Which number, which natural number into itself 6 times can give you 64?
Ma'am, I think it's an imperfect cube.
No, it's not. It's not about cube root. It's the sixth root. Sixth root.
2. Ma'am, 2, ma'am.
Who said 2?
Ma'am,
Who said 2?
3, ma'am.
2. Netra said 2. Uttanshri, then
Ma'am, I said 2.
Madhumita is it? All right. 2. All of you multiply 2 with itself 6 times. All of you check 2. What's the answer, Giant? What is 2 multiplied by itself 6 times? What's the answer?
Ma'am, 36.
No.
64.
2 into 2 into
64,
2
ma'am.
into 2.
64, ma'am.
What is 2
64.
and 2? 4. Watch my screen. Watch my screen. What is 2 into 2? 4. 4 2s are 8. 8 2s are 16. 16 2s are 32. 32 2s are 64. 64. So the sixth root of 64 is 2. See here. The sixth root of 64 is sixth root of 2 into 2 into 2 into 2 into 2 into 2, 2, 2. Correct? 1, 2, 3, 1, 2, 3. Yes.
6 times, ma'am.
4, 8 2s are 16, 16 2s are 32, 32 2s are 64. So from 6 2s, because sixth root, no? Sixth root. So from 6 2s, 1 2 will come out. If it is cube root, from 3 equal numbers, 1 number will come out. If it's cube root. No, don't flip the pen like that. All of you should know how to behave in a classroom. No flipping, no flipping, no adjusting your hairstyle. Fasten your hair. If you have to keep adjusting your hair, fasten your hair. Yeah, children. So let me different number now. Now, supposing sixth root of 729. Okay. Am I taking a too large number? No, let me go back to the Sixth root of 64. Let's understand this, the same thing again. It's a sixth root of 2 multiplied by itself 6 times. 2 multiplied by itself 6 times. From 6 2's, 1 2 comes out. Oh, sorry, 1 2 comes out. So the sixth root of 64 is 2. Do you all understand this answer? The sixth root of 64 is 2.
Yes, miss.
Yes, ma'am.
Yeah, because when you multiply 2 with itself 6 times, not 2 into 6, 12. 2 into 2 into 2, 6 times will give you 64. So the sixth root of 64 is 2. So children, what am I trying to say out of this? I'm trying to say that whenever you find a square root or a cube root symbol, doesn't mean it's an irrational number. See, when you find square root of 25, this is 5. 5 by 1. It's rational. It's rational. But if you find square root of 30, no, it's an imperfect square. So this one will be a non-terminating, non-repeating decimal. It's an irrational number. Now you'll ask me, tell me what is the square root of 30? See, all these values, you cannot have it in your mind. It's not like tables, like 6 5s are 30, I can tell you like that. Okay, so the square root of 30, because 30 is not a perfect square, the square root of 30, its value will be a non-terminating, non-repeating decimal, and so it's an irrational number. When you see cube root of, say 64, it's 4. Because 4 4s are 16, 16 4s are 64. Which is 4 by 1, rational. But if you find cube root of 100, cube root of 100, cube root of 100, no, there is no number which when multiplied by itself 3 times can give you 100. So it's a non-terminating, non-repeating decimal. Irrational number. The cube root of an imperfect cube is an irrational number. The square root of an imperfect square is an irrational number because its values are non-terminating, non-repeating decimal. Because its values are non-terminating, non-repeating decimal. Now, children, tell me, is this a rational number? Is this a rational number?
No, ma'am.
No, ma'am.
No.
No, ma'am.
Why?
Ma'am, the square root of 5 is not an integer.
Very good. Correct. Because it looks like something by something. But what is a rational number? It should be integer by integer, not simply something by something. It should be an integer divided by an integer. Is root, so let's write, see now again, let's write integers. So -3, -2, -1, 0, 1, 2, 3, like this, the collection goes like this. These are integers, these are integers. And we know integer by integer is a rational number, is a rational number. Is this an integer? I don't see this in the collection here. Root 2, I don't see root 2 here. It's not an integer, this is not an integer. Is root 5 an integer? No, I don't see it in the collection of integers. It's not an integer. So simply because it is something by something, it does not become a rational number. It is not in the integer by integer form. It is not a rational number. It is an irrational number because 2 is an imperfect square. 5 is also an imperfect square. So by now you should have understood what terminating decimals are, non-terminating repeating decimals, how to recognize them, how to recognize terminating decimals, non-terminating repeating decimals, non-terminating non-repeating decimals, how to recognize them. And you know that these two are outcomes of a P by Q, of a division process. When you divide P by Q, you may get a terminating decimal or a non-terminating repeating decimal. Now, this one is not an outcome of a P by Q. No, it's not an outcome of a P by Q. It's the square root, the value, the square root of an imperfect square or that it's not only these, there are many more children. Just for your standard, this is enough. Cube root of an imperfect cube. And I gave you a different example. 6th root of 64 is 2, is a rational number. But the 6th root of 50 is irrational, The 6th root of 50, because there is no number which when there's no natural number which when multiplied by itself 6 times can give you 50. So from this 6th root of 50 is an irrational number because its decimal expansion will be non-terminating, non-repeating. Okay, so now just a minute, children. So rational numbers have a p by q form. They have a terminating or a non-terminating repeating decimal expansion. Irrational numbers do not have a p by q form. They have a non-terminating, non-repeating decimal expansion. Class, use the emoji, raise your hand. Use the emoji, raise your hand, class. Raja, Sindhu, Sanjay, Devadarshini, Madhumita, Krishmika, Udanshri, Gautam, Netra, Krishmi, Jayant. You don't have the emoji? All right. Now, children, look at this one. Now, when I look at 1 by 8, it may have a terminating decimal or a non-terminating repeating decimal, correct? Because when you divide 1 by 8, you don't know if the division will come to an end or will not come to an end. If it comes to an end, it will be a terminating decimal. If it does not come to an end, it will be a non-terminating repeating decimal. Please understand that. 1 by 8, when you divide this, if the division comes to an end, it will be a terminating decimal. If the division does not come to an end, then it will be a non-terminating repeating decimal. But it will be one of these two. It will not be a non-terminating, non-repeating decimal because that is only irrational number which does not have a p by q form. See, 1 by 8 is p by q form. So this will have only two kinds of decimal expansion, either terminating decimal or non-terminating repeating decimal. If the division ends, terminating decimal. If the division does not end, non-terminating repeating decimal. It will not be non-terminating, non-repeating because that is only for irrational numbers. This one is a rational number. Now, what we're going to understand is that, without dividing, you're not going to divide. Just by looking at the number, you can say if it has a terminating decimal expansion or a non-terminating repeating decimal expansion. Now I look at this 1 by 8. It will have a terminating decimal expansion. So there is some method. Now supposing 3 by 125. See, I don't know the value of 3 by 125, but I know it's a terminating decimal. Now say 7 by 40, terminating decimal. See, I'm just giving you random fractions. I don't have anything beside me. I'm not using a calculator. So now say like 33 by 200. We'll have a terminating decimal expansion. See, who can remember 33 by 200? Or who can remember the value? How can I always remember what is 7 by 40, 1 by 8, 3 by 125? It's not possible. So there is some method. from which you can make out without dividing. You can make out if the P by Q will have a terminating decimal or a non-terminating repeating decimal expansion. I'll tell you how. Now 1 by 8. Is it in the simplest form?
Yes, ma'am.
It is in the simplest form. Children, I think after this class we'll start working, meaning I will be talking less and you will be working more. So the introduction is too much in this chapter and we are doing it slowly. So you might think that I'm going on and on talking. So next class onwards, you will have more work than me. Listen to all this carefully. 1 by 8 is in the simplest form. That's the first thing you should do. You should put it in the simplest form. Now write 8 as a product of its prime factors. 2 into 2 into 2. That means it is 1 by 2 cubed. Correct? So now look at the denominator Q. We call the denominator as Q. P by Q form. No, so Q. Now Q is equal to 2 to the power 3. It can also have a 5. It can also have a factor 5 with it. Let me take that example first for you. 1 minute. Now supposing I take 1 by 40. 1 by 40 is 1 by 2 into 2 into 2 into 5. That is 1 by 2 cubed into 5. So the denominator Q is 2 to the power 3 into 5 to the power 1, which is of the form 2 to the power m into 5 to the power n, where m and n are whole numbers. M and n are whole numbers. Therefore, 1 by 40 has a terminating decimal expansion. 1 by 40 has a terminating decimal expansion. That means after putting the fraction in the simplest form, express only the denominator. Don't see the numerator. Numerator can be anything. Write the denominator as a product of its prime factors. If there are only 2's and 5's in the prime factors, only 2's and 5's. See, there can be only 2 or only 5 or both 2 and 5. It can also be only 2's or only 5's or both 2's and 5's. If the prime factorization of the denominator has the prime factors 2 and 5 only, then that P by Q will have a terminating decimal expansion. See, what is the terminating decimal expansion? We are not finding. What is the value of 1 by 40? Now I'm using the calculator. 1 by 40 is 0.025. That you cannot say, but you can say that it has a terminating decimal expansion, 0.025, finished. The value of 1 by 40 is actually 0.025. See, it's a terminating decimal. So that you can say, it has a terminating decimal, you can say. But what is that terminating decimal? There's again another shortcut for that. We will see that only in 10th standard. There is a shortcut. What is that value? How do you find 0.025? For that also, without long division, you can find out. But that we are not going to understand this year. For now, only this. Not this. Am I clear, children? We'll take a few more examples, but is this understood?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Let's visit the same sum again. So I said 1 by 40. It's already in the simplest form. Supposing I gave 2 by 80. Then you must cancel 2 ones are 2 40s are. So 1 by 40. Simplest form 1 by 40. So supposing I gave 2 by 80, you must simplify 2 ones are 2 40 times. So it's 1 by 40. And forget the numerator. Don't find, even if you can, don't find the prime factors of the numerator. Find the prime factors of only the denominator. And you can see that it's made up of only 2's and 5's. That is, the denominator Q is in the form of a product of the power of 2 and 5 only. I told you there can be only 2's, only 5's, or both 2's and 5's. So we say that it's in the form 2 to the power m into 5 to the power n, where m and n are whole numbers. Because here 3 is a whole number, 1 is a whole number, m and n are whole numbers. If the denominator is in that form, if it's in the form 2 to the power m into 5 to the power n, then that p by q will have a terminating decimal expansion. Now let's take another example. Say 7 by 54. Is it in the simplest form?
Yes, ma'am.
Yeah, it is in the simplest form. It is in the simplest form. So now let's find the prime factorization of the denominator 54. 227 times 3, 3s are 3, oh, 3 9s are 3, 3s are 3 1s are. So this is 2 into 3 cubed, correct? So Q is not in the form 2 power m into 5 to the power n, correct? That's all you can say. Because 2 is there, but there is 3. There can be what is permissible, only 2 and 5, only the primes 2 and 5. There is something other than that. There is 3. So 7 by 54 will have a non-terminating repeating decimal expansion. If there is a prime factor other than 2 or 5, it will have a non-terminating repeating decimal expansion. Let me use the calculator and tell you what is 7 by 54. 7 by 54 is 7 by 54. My calculator says is 0.1296. 1296. 296, 296 goes on like this. So what is recurring? 7 by 54 is equal to 0.1296 recurring. See, I use the calculator. 7 by 54. 7 by 54 is 0.1296. 296, 296, it goes on. My calculator can show 12 digits. But we see the pattern here. See, 296, 296, 296. That's all. It's confirmed. It's 296 only forever. Don't put a bar on 1. Don't put a bar on 1. 0.1296 recurring. So this one has a non-terminating repeating decimal expansion, and you can see it here. It's non-terminating repeating. Because 2 is there, but 3 should not be there. But 3 is there. Then it is non-terminating repeating. For example, 8 by 125. So this is 8 by 5 into 5 into 5. So 8 by 5 cubed. 8 by 5 cubed. So the denominator q is, if there is no 2, you can write it as 2 to the power 0, because anything to the power 0 is 1. Anything to the power 0 is 1. Anything to the power 0 is 1. So the absence of 2 can be shown like this, 2 to the power 0 into 5 cubed. So it's perfectly in the form 2 to the power m into 5 to the power n. See, there 2 factor is not there, but you can show it using 2 to the power 0. Because m and n are whole numbers, right? M and n are whole numbers. 0 is a whole number. So 8 by 125 is 8 by 5 cubed. And 5 cubed is nothing but 2 to the power 0 into 5 to the power 3. It's perfectly in the form 2 to the power m into 5 to the power n. There is only 5, there is no 2, but you can write 2 to the power 0. So it's perfectly in the form 2 to the power m into 5 to the power n. So 8 by 125 will have a terminating decimal expansion. 8 by 125. So my calculator says 8 by 125 is 0.064. That's it. Terminating decimal. Terminating decimal. Okay, so like that, children. So if the denominator has anything, see the denominator may have 2 to the power 3 into 5 to the power 2, but something extra like this 7. No, non-terminating repeating decimal expansion. There should be nothing other than 2, 5. There can be 2 cube, there can be 5 square, but there is a 7, non-terminating repeating decimal expansion. Supposing the denominator is 2 to the power 4. Supposing the denominator is 2 to the power 4, terminating decimal. Supposing the denominator is 5 to the power 5, terminating decimal. Supposing the denominator has 2 cubed and 5 squared, terminating decimal. But if it has something other than 2 and 5, that fraction will have a non-terminating repeating decimal expansion. Is that understood, children?
Yes, ma'am.
Yeah, now this is your homework. Without actual division, find which of the following rational numbers have a terminating decimal expansion. You should not divide. Fine. Without division, you should find which of the following rational numbers have a terminating decimal expansion. So I'll just do the first one for you. First is you should put it in the simplest form. Put it in the simplest, sorry. Put it in the simplest form. 15 by 96. You can cancel by the tables of 3. 3 5s are 15. 3 32 times. First, you should put it in the simplest form. That's very important. If you forget that, you will go wrong. Next, write the denominator as a product of primes. So 2 into 2 into 2 into 2 into 2. So which is 5 by 2 to the power 5. That's all. You don't have to show any more steps. If you're interested, you can show this. Q is equal to 2 to the power 5 into 5 to the power 0. 5 is not there, no? So 5 to the power 0. So it is in the form 2 to the power m into 5 to the power n, where m and n are whole numbers. M and n are whole numbers. Therefore, 15 by 96 has a terminating decimal expansion. You can just take a screenshot of this slide. Complete these sums as homework. We'll see the answers in the next class.
Yes, ma'am.
All right, children. So that's it for today's session. Thank you so much. You may leave the meeting.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you.